experience in ERC grants, has done them all, so he's at the last ERC grant right now. And he's actually a professor at the University of Liverpool and has been doing some work there at the Center for Material Discovery, which I remember visiting maybe 10 years ago or so, which was a center that the University of Liverpool had in order to speed up discovery of new materials, of new functional materials. That was a very interesting work at the time. They were pretty much focused on high throughput methods. And I believe that artificial intelligence and evaluations and computational work is something to speed up that as well. So Alessandro will tell us and talk us about digital material discovery in organic electronics.
So thank you very much for the introduction, and thank you very much for having me here. It's great. I think we should really talk a lot about how we organize into institute where different background comes together to develop digital methodologies. That's ours. It's called the Materials Innovation Factory. When I was appointed in Liverpool, I was shown the building wrapped into building construction, and one of the pillars of the building was computer-aided materials discovery. Was what I wanted to do. Therefore, I was convinced by the institution to move there because the idea of having together engineers, chemists, physical scientists, developing technologies to discover new material is something very attractive to me. I was traditionally focusing to developing models, physical models, and then I sort of missed the opportunity to see my model translated into real discovery of materials. This was the reason for moving, and also a thread in my lecture. Let's see how it is possible to have through digital discovery tool the discovery of actual material. So what you need to do to make sure that your predictions are realized as quickly as possible. People that have done work, at least there, Marcos, Omen, Kaire, Daniele, and Shiwen are the main players here, plus funded. Maybe I should mention of two recent initiatives that are happening in Liverpool, so if you want to visit. So we are one of the AI Hub in Chemistry, recently funded, started 2 months ago, so will be one of the centers in the UK for AI application in chemistry. And I'm now the director of the Center of Doctoral Training in Digital and Automated Materials Chemistry, very long name, but we are planning to train 90 PhD students in the area of digital methods in chemistry in the UK. So if you have a good student who wants to do a PhD with us, you can send them. What the main point is here, who is going to become a focal point of research in this area in the UK. This is not working. The topic is, of course, of this workshop is more about the methodology of machine learning rather than specific of the application. So I have only one slide on the application, which I will focus on, is organic electronics. There are several posters down there. Professor Ferreira is expert in CICECO. For our perspective, if you don't care about it, is we're looking for molecules or polymers to perform function in devices. In a review, recent review, we made a very long list of devices that we want to make with molecules, and I'm going to list any of them. There are some cartoons, but solar cell, sensor for bioelectronics, thin film transistor, flexible device, this kind of thing. The main point of this table is that the list of applications is increasing. Every year there are 2 applications more, and this list is becoming old. As soon as I brought it, it was old. The point is that organic electronics is so varied as a field and broad that you need a general tool to discover organic electronic material rather than focusing on one particular application and develop all the technology for that particular application. So our goal was to develop a general tool or set of tools that work throughout the field of organic electronics, meaning discovering materials for organic electronics. So, I'm organizing this talk by doing this flowchart and telling you what we decided to do, for what reason, what was the problem, and so forth. Given the topic of this workshop, I will spend the majority of the talk to discuss AI methods, but I will also mention the others which are related to algebra screening and physical models. As we've seen from the talk before, they are part for the AI, and again, algebra calculation are also part of the AI, because if you don't generate good quality data, you cannot do AI. So even when I'm not talking about AI, I will be talking about AI in some sense. So the first question we ask, we want to find the material with the right properties. Is the physics simple enough that I just compute the property and see if I can find the right material with the right property? So surprisingly, there are a number of properties that we are searching in material which are simple enough that we can simply compute them and compute them for lots of molecules and find the molecule we want. So this is the concept of virtual screening, something as old as computational chemistry, something that we can say was pioneered by the pharmacists. They've been there before us, have more money in pharma than in materials chemistry. And so the idea is that you consider a very big set of molecules. You predict through virtual methodology their properties. In case of pharma, their drug activity. In case of materials, their electronic properties of what you need. And then through a series of calculations and increasing degrees of accuracy, you will find hits that you will test experimentally. So initially, we started when we used, the community started by imagining molecules substituting in random fashion, so molecules that you can think of or molecules that can be made. We decided instead to increase the chances that our experimental colleague will follow up on our suggestion, to consider molecules that were already made, but for other reasons. The plan was that if we could find useful molecules that were already made for different reasons that are useful for organic electronics, we would convince people to take them up and discover very effectively and rapidly something useful. So we started a series of work. And the plan was to do only one virtual screening, hopefully to look for a range of useful properties that could hit different targets with a single job. So we started with considering 40,000 molecules that are already available in the Cambridge Spatial Database, so we know how they are arranged in a solid state. And the plan is that if we consider, for example, the number of molecules with small gap between home and room, so the semiconductor, the plan was that if we could find that this set is totally unbiased, meaning it was not built to satisfy any particular design rule. Therefore, we could find hits or molecules that satisfy particular criteria which we are not considered before, and we are not even within the set of molecules that we are going to be considered because they had a different design rule. That was the idea. So we started with what seemed a very cool application at the beginning, singlet fission. So we were looking for molecules such that the energy of the singlet is more than double the energy of the triplet. It is very rare. Properties less than 0.5% of the molecule has it. And the molecule with this property can be useful in a solar cell, for example, because you can hit a molecule with a photon, they generate two excitonals, so you can generate double the current for the same device. That was our first application. Then we realized that, yeah, we have a database, we can search for a lot of other things. So we search for molecules where the singlet is very close to the triplet. These are used for luminescence application, temperature activated delay fluorescence, or molecule which would work as an acceptor in organic solar cell, alternative acceptor that people have not thought about them. You can see from the way it has been presented, I will not talk about any of those topics in particular. The reason is that despite having reasonably good paper out of them, maybe some decent citation and so forth, we realized even if the molecule were available or made by someone already in the past and the synthetic pathway was present in literature, it was difficult to convince people to look at them. Simply, it's not appealing for an organic chemist to repeat the synthesis that was done in 1996 for a different reason, because it will not look new to them, they're not excited about it at all, it's not part of the chemistry they do. And so while I'm very confident of this prediction, and in fact some of them can be verified later, we realized that this is not the right way to engage with the community. Remember, I want to have impact, so people should change the way they behave in the lab through my work. So we changed the strategy, and instead of looking at molecules that were made at some point for some reason, we decided to look at molecules that you can buy. The idea is that if you can buy, you cannot tell me no. How many molecules you can buy? You can buy 12 billion molecules that if you order them now, they'll reach your lab by the 16th of April, so this month, of May, this month. So 2 weeks delivery time. If you select this criteria, there are about 12 million molecules you can buy. So we decided to compute the electronic properties of all the molecules you can buy, and create therefore a tool for people to buy the molecule with the property that they want. Of course, we exploit the work done by the pharmacists before us. The molecules you can buy are mostly meant for the drug discovery community because that's why they're made. So they're biased totally away from organic electronics. Still they're there. In blue here, these are calculated versus experimental excitation energy, singlet per singlet. In blue are calibration curves, so data from literature, and our methodology is the TDFT routine calculation. In red, there are a few molecules that we bought and we measured to show that the error in our prediction is controlled. So this is the error, we cannot do better unless we develop better technology. And as an example, I'll tell you something we did to discover dual emitters, so molecules that emit from two different excited states. This is the only example I show today. So I don't know if you've ever done a module in photochemistry, but I remind you that normally molecules don't emit from higher excited state. They all emit from the lowest excited state, S1, just because when you excite the molecule in higher excited state, they will immediately relax to S1 and emit from there, or not emit at all. The only way to emit from two states is if there is a big gap between S2 and S1. But we've computed them all, so we have them. So we can simply look at our database of what you can buy and look for molecules that have a very big gap between S2 and S1. In this cube here is a distribution of the relative gap between S2 and S1 of all the molecules in the database. And in red, there are the known experimental molecules that emit from S2. You can see they are very predominantly in this area. So if we look for molecules with very large gap, there are good chances of finding the real one. And now I did something that as a physical chemist or a physicist I never did. I introduced the parameter, the cost of the molecule, because we have that as well. So we just can rank them by cost and buy the cheapest. So we bought the cheapest molecule. They arrive in a box, but we're a theoretical group. We don't have a fridge. We don't know what to do with them. So I asked the student to figure out what to do. The student, I don't know how, where, what, find the spectrometers when they are measured and find a molecule that is a dual emitter. So a property which is extremely rare, 1 out of 1,000 molecule, was found by a group of theoreticians without the lab. So the point is that if you do efficiently, you mentioned breaking the barrier between digital and experimental. If you consider in the digital search that you should break the barrier, it should make it very easy for your discovery to become something testable in the lab, you can reach the situation where even a theoretical chemistry group can do experiment and discover new molecules. So we were excited about it, and also middle-aged crisis, I'm older than Alessandro. We went for our conventional site. So we have a project where the idea is you can search for molecules with the desired combination of properties. I want it green, I want it with a low LUMO, I want it soluble, that kind of things. Reverse search of what are the molecules in the current chemical supply chain, and within the same platform you can order the molecule and get them in your lab. This is in the EU jargon, it's close to MySol 2. So we are recruiting beta testers for this platform. So if some of you are in the organic electronic business and you want to have a go for free, you can register as beta tester or let me know, and you just do your research with this and you get your molecule and tell us if it works or if it doesn't. That's the virtual screening part. Of course, a lot of attention by the machine learning person of accessing the database and extracting information, but we're taking a different direction now. What if the property we are interested in is not as simple as computing the excitation energy, HOMO and LUMO and so forth, or something more complicated? That's my job. It's what I've been doing for 20 years. It will continue to be my main job. We approach this process through model reduction. Take the detailed computational study of the problem, reduce it to the basic physical principle, derive a physics-based model, do the model, and so forth. So, not the topic for this workshop. My main expertise in transport property, electron transport in organic materials. And so we have a set of tools, which I will not give any details about, on describing how electron is transported in the molecular semiconductor. We also work on polymeric. Let's only think about the ingredients in this calculation. The ingredients are the electronic structure of the molecular crystal, vibrational structure, because electronic and vibrational modes or formal modes are coupled together for transport. Then you also need a theory for transport. That's not easy at all. It took 20 years of fight within our community to come up with a great theory. There is a summary if you're interested in a recent review. But we have all the ingredients. And now we can actually use virtual screening with the ingredients coming from our physics reduced model to do screening. We start again from the Cambridge crystallographic data center, so the Cambridge database. Again, we reduce it to the semiconducting molecules, it's 40K. Reduce a little bit to the molecule, which have a nice 2D network of interaction with other molecules. There are still 5,000. So for 5,000 molecules, we come up with a number of tricks to evaluate the vibrational structure, the electronic structure, and then the transport, and identify ion mobility from that. This is reported in the paper. What is exciting is that the Cambridge Data Center was made aware of this paper, and now they decide to introduce in their data center the descriptor of this crystal. So if you, next time you deposit the structure, whether you want it or not, this property will be computed and so it will be available for everybody. So if you do machine learning, you can use, and by the way, they're also available in a human readable version if you want to have fun with them. So what do you get out? Of course, if you screen, you find high-performance material. Molecules have not been considered, but there's very small number, maybe not the greatest output there. Something else that you get out is a structure property relationship. So what makes the best material the best? And then you can rank these properties, giving insight to the experimentalists as in what they should do. For example, the most important property is the unit cell area. So the larger the unit cell in 2 dimensions where the transport takes place, the larger the mobility. Looks weird initially, but is of course based on geometry. The unit of mobility is centimeters square per volt per second, so the dependence on the square of the area is intrinsic in the scaling of these properties. And the only important property here is a dynamic disorder, which is the fact that molecules oscillate around their equilibrium position and distort the band structure because of this oscillation. And this is the key property for high mobility molecular semiconductor that emerged now statistically for studying 5,000 of them rather than fighting or my model, your model, these two systems against your two systems, and then having endless discussion about the physics of this material. So having a large data set will inform very robust derivation of a structure property relationship. And finally, I want to mention this because it's relevant for this community. Once you study a lot of them, and I would argue that 5,000 is essentially all of them, covers even the one that have not been made yet, you can predict what is the maximum performance of this class of material overall in the future. Because what you can do is you look at all the parameters that make the mobility in this case, and then say what would happen if each one of them is optimal. Optimal means top 5%. So you can generate a thought experiment where you find the other material where every single parameter are optimal after you verify that they're not anti-correlated, of course. And therefore you can even establish what is the maximum performance achievable of the entire class of parameters because you've studied enough of them that you know what can be achieved and what cannot. So, if it's not simple and you can do model reduction and things become computable, then a lot of things become possible. You can establish feasibility of certain technology, intrinsic limitation of technology, structure property relationship. But of course, there is a possibility that what you are trying to predict is not directly computable. I want to spend one slide to give you an example of this, because it was a project we ran several years ago to discuss the microscopic structure inside an organic solar cell. It's made by a donor and a receptor organic material combined together, like this one. And so to create a microscopic model of this system, we have to write papers studying the crystalline, semi-crystalline microstructure of PDHD, the polymer used there, a couple of papers. Then another paper to study the amorphous microstructure of PCBM, which was the donor used at the time. A paper to study the interaction between them and the interface, microdynamics, equilibration. A paper to study the electronic structure. There is a non-periodic, very large material, because it wasn't possible with existing technique. So the result of this is 40 years to study materials. By the end of the 40 years, nobody is be looking at anymore because people have found different acceptors, different donors, and so forth. So there are problems which are difficult also because the community is moving very quickly around them. So there is no benchmark material, there is no reason to study them too efficiently. So maybe David is happy because he found a job as an academic in Ireland. The other David McMahon is happy because he got a postdoc at MIT, very nice for him. Maybe he got my paper, so the founder is happy, but I'm not happy in the sense that I've influenced how the field has moved. Even when I consider one of the main achievements of our project on organic solar cell, when I wrote this incredibly bold title, what makes Fourier exceptions spatial and how to replace them. I mean, I've never write a title like that anymore. 12 years ago, I even predicted how the molecule should be made to become an acceptor. Okay? Then a few weeks later, someone makes essentially the same molecule, a dimer of the very same molecule with the separation there. Was this the right prediction or not? I'm very cruel against myself. I think that as a tradition, we are completely blind. And so if there is evidence which support our prediction, we believe it. If something is really not supporting a steady state of experiment, it's not really important. I didn't really mean to be interpreted this way. So what is the true way of validating a theory? It's not just this by one-to-one component. So we enter in the world of data science and machine learning because we wanted to be more honest to ourselves. We wanted to see if our prediction of what makes a good acceptor was valid. So very difficult to collect data from literature. We have from Alessandro, how challenging, how inconsistent. So with a trick, we employ undergraduate students to do that. They are almost as good as language recognition. If they know some chemistry, in this case, Alina New, top student of year 3, she collected a number of electron acceptors, and we used her, at the time, a smallish collection of 79 acceptors to check our theory, which was that the good electron acceptor have a very small gap between LUMO and LUMO plus 1, so a very unusual property that nobody has looked at. And so we realized that through collecting data, it is possible to verify hypotheses working in a convincing way rather than hand-picking case that will validate your theory. this was the beginning of our journey in using machine learning for discovery of material in organic electronic and solar cell, because we thought, yeah, this is only one-dimensional correlation plot. We showed that one parameter is important. Can we do better? Can we predict the efficiency of solar cell by looking at more parameters, larger data, through a machine learning approach? So the reminder of this lecture is then how do we deal with the situation where we have a large number of data points, experimental but heterogeneous. We like to find the best material that replaces the one already out there. This slide is completely trivial for all of you, but I didn't want to remove it. The idea is to use machine learning to predict the outcome of some proposed experiment. And of course, the initial challenge, and the only challenge, if this is the question, is how do we digitalize the experiment and the data? As I mentioned, the digitalization is carried out by very patient students. We believe it was impossible at the time. Maybe now it's more possible to scrutinize the literature. We always wanted to give full transparency, the reference for every single paper. People should be able to check. And so we collect them manually. And also, what you collect from this experiment is also something that can vary, because we can look at physical properties, chemical descriptor, some combination. For machine learning, we are very boring. We don't know very much about any method, therefore we use them all. An example, and then we see happiness, and then some issue, and then maybe more or less will be for my conclusion. So, initially, 2018, 280 molecule experimental organic photovoltaic devices, we collect them, all based on small molecules because polymers were too complicated. Bucket junction, so we consider the efficiency, PC, as a figure of merit, and the first attempt was to use the physical descriptor of this system as a descriptor, meaning for donor acceptor, we look at the electronic properties, and so we have an array of electronic properties that form our input for the machine learning, those. The green one are what everybody knew, very important for like electronics, the alignment of energy level, the steady state. The blue are features which emerge from various theories that people thought were important. Then gray, we suspect it could be important, we're not sure. And black, something we introduced therefore for this work. The methodology, being non-expert, was simply going through the various methodology, trying to read as much as possible of how cross-validation needs to be done, then fold. We also try to leave one out. And quality of learning, again, wasn't completely clear what we should measure. But at the end, it doesn't matter, you pick your favorite, but what is the best method according to a measure is the best also according to the other measure, so it's not going to be too critical. When we present this table, the impression of this table is different when you look at it a few years later. We said at the time that this methodology, gradient boosting, part of the family of tree models, was reasonably good, with good parameters, error on the efficiency 1%. 1%, we're talking is essentially 10% of the typical efficiency of the best one, which is 10%, so it's not 1% accuracy, relative accuracy. Reasonable correlation factor, although you can, the people are working on this field for longer. I may have spotted something which is worrying, which is a KNet is just a little bit worse. So this means that the methodology that simply find a molecule which is as close as possible to the other in terms of physical parameter is performing almost as well as an advanced multi-decision network tree. Something that I'll elaborate really in the next few slides. But at the time we were more optimistic, and so we presented this plot as an excellent result. So we can predict the efficiency of solar cell having a model which accepts as an input parameter of the component and having this performance as an output. We wanted to improve things, and we said, okay, not just only physical parameter. Why don't we describe the chemistry a little bit better? Why don't we add fingerprinting of the molecules here? So this is standard way that pharmacists use to translate a molecule into an array of 1 and 0 that tell if the functional group is present or not. Introduce a distance between molecule, again, very conventional medicinal chemistry application. So again, we have issue in inventing anything new here. And then the methodology. Methodology really is a standard methodology that allow you to predict a property if you have an array of property predicted for a number of structures, very heterogeneous properties there. But if you can define a distance between the molecule in the input, then you can predict the output. So it's Cambridge regression, and the key element is having a measure of distance between two data points. So if I have two photovoltaic systems, donor acceptor, various combination of chemistry, if you have a way of estimating the distance between them, so that it's 0 if the systems are identical, it's very large if the systems are different, this is the method you can use. And the other parameters are essentially how are you going to weight the distance in the different direction, different dimension of your screening. Here we can have the chemical fingerprint, the orbital level, so electronic properties, the efficiency is what we are predicting, but also short circuit current and other properties of the device. Other parameters are what describe the system, and the output looks more or less like the one I showed before. When moving from left to right, we are increasing the number of descriptors, so we are adding chemical descriptor fingerprinting to the physical descriptor. So the point of this experiment was to show that if you add the chemistry to the physical description of your component, your ability to predict the efficiency of the device, increases. But, as already alluded to several times, are we just doing an interpolation here? Because we are really mapping, saying that something is predicted to have a certain efficiency simply because it's close enough in chemistry and in physical property to something that is already in the database. What is the level of information that we extract from here? Before reflecting, we continue a little more before realizing what could be wrong with this. And this is the work that Daniele and Padula did. We realize, of course, that the system is made by donor and acceptor, and for a reason that you can imagine very well, for many years people have tested very few acceptors and changed the donors, or they fix few donors and they change the acceptor. So the data are distributed in a very unusual fashion, where people tended to change only one of the components of the organic electronics device, or the organic solar cell, and therefore it looked impossible in this situation to really predict the efficiency of unusual combination of donor and acceptor. So Daniele was playing with this, and he wanted to rephrase it in terms of the Netflix challenge, which at the time it was popular, and maybe some people have forgotten it. His challenge is to predict whether you will like a movie or not, based on how well you liked the movie that you watched, and how well other people have liked the movie that they have watched. So essentially, in this case, acceptor and donor, the acceptor are the user that has scored the movie, whether they liked it or not, and the number of movies is much larger, of course. And so each user has scored few movies, and each movie has been scored by several users, and therefore predicting what will be the way you will score a movie is very important to Netflix, because they want to propose a movie that you will like. So this matrix filling problem is very old, just a nice way of putting by Netflix, but it's already out there. So we decided to use our algorithm as a matrix filling problem, and to see if we were able to predict the efficiency of mixed donor and acceptor exactly with the KRR method, introducing again a distance between donor and acceptor. something which was surprising, published well, but we should have been worried a little bit about it, is that we have now increased the dimensionality because we are changing two components of our device, and the prediction is better. The data set is a bit larger, the prediction is slightly better, and so it's either the methodology is amazing or there is something that we are maybe missing. Another element that helped us maybe in the right direction was when we tried, this is more recent, to have more descriptor and more data. So she went, coming from China, extremely patient young student, manually collected a data set of 566 donor receptor pairs. She was helped by the fact that the field at the time was re-exploding because of the new electron acceptor, and decided to expand the number of descriptors to include something that we believe was absolutely essential, the miscibility of the donor and receptor, physical property of them, and the performance of that was essentially the same as before, the same as when we had fewer descriptors, even if we included descriptor that have strong correlation with the property we were computing. The reason is that these new descriptors that we are introducing are already encoded within the chemical fingerprint or the other descriptor that we have. So we're adding descriptor highly correlated with the efficiency, but also highly correlated among themselves. So once you have fingerprints describe almost all the physical properties of the material in terms of miscibility and thermodynamics. In fact, there are machine learning methods that describe the miscibility based on fingerprints. So if your fingerprints are in the data set, adding miscibility information will not add anything. So here we went back to what I said before. Something we should have noticed in the first paper is lab paper number 5. The performance of KNN methodology is almost as good as the other method we've done, support vector machine and K-knowledge regression. So this means that a methodology which simply makes a prediction based on the efficiency of the solar cell is the same as the efficiency of the solar cell closest to it, as trivial as that, is not bad. What is the problem? The problem is that chemists copy each other a lot. So our database does not contain copies, but as soon as someone here in Aveiro makes a nice molecule, someone in our country I will not mention will make the same molecule with the fluorine attached to it, with the methyl attached to it, produce results which are almost the same, and therefore our data set is made by a lot of molecules which are almost the same, which give exactly the same result. From the point of view of scientific reproducibility, this is amazing. It really means that there is no fake result in this area, because everybody is going to repeat and reproduce and do almost the same. So if it's fake, it will be spotted a few months later. But from the point of view of machine learning, it's terrible, because now we have data set where things are there many times. There is no training and testing set. I take away 10%, it's already there in the data set. So there will be not data leaking, but effective data leaking. So how do we measure it? We are fortunate in the case of organic photovoltaics, because chemists also helped us by classifying their acceptor depending on their chemical structure. So all the electron acceptor used in organic solar cell can be divided into groups depending on which functional group contain more than 50% of the LUMO density. LUMO is what is accepting the electron, so it's relevant. If you have more than 50% of the LUMO, we'll find what fragment of your acceptor is the chemically important one. So Gwen again managed to identify 5 groups. So divide the data set of all acceptor into 5, and now it's not a random separation in trial and testing system, but it's a specific grouping into different classes. And then we can ask the question, would you have been able to predict that this is a good family if we only know about the others? So we can actually ask the question, which is the real question, can this methodology predict completely new chemistry, because we don't really care about adding a methyl group or a fluorine here and there to find something slightly better? And the answer is that the methodology, as I showed you, looked so successful, is not, as it is, actually able to predict this new class. So we have called trivially, I know many people don't like this, dividing interpolation versus extrapolation. Extrapolation means can you predict an entire new class if this has been removed from the thing? And we realized that what looked particularly good, if you include fingerprint and physical properties, is actually horrible. Horrible to the level of randomness decision. So like you predict random things. So if you remove the training element, the thing that looked fantastic is not as fantastic. Then we try to retrain everything to make it better at being a better extrapolator. So we see which one will extrapolate better. And now, not surprising, it's much better if you remove completely the fingerprint. Because the fingerprint was confusing the argument. The argument was looking for something which was similar chemically and saying if it's similar chemically, then it same properties. Now it's only physical. Now it can generalize better because things which have the same energy level are hopefully having the same electronic properties in the device. And so we have done something slightly better, but not as good as before, to extrapolate. It's based on physical descriptor, and now it does measurably better than randomness, but not as good as publicized in our earlier work. Now something which I'm shocked, and I would like to discuss at dinner tonight, is what happened when you publish paper where you believe things are going fantastically well on very top journal, and when you publish paper when you say that things are maybe not as good and need to go to a technical journal. And so at the end we have the literature where top results, top journal, useful result, bad journal. And so at the end we have the perception that machine learning is always working great without the opportunity of discussing. So I'm happy to have the chance to tell you this. Can you remind me how much time I have? Finished? Okay, then I'm going to mention one. No, I skipped this. I didn't mind to ask this. And so I will only tell you about this, but only the concept is finished. I wanted to really understand if this method were useful or not. And so based on the idea that the data are limited, always will be limited, or I'm considering a system where the data will be expensive to make. I'm considering the fact that the literature is biased, entirely biased by the story I told you. Herding behavior is called in social science. People follow sheets. And then there is a physical explanation. See, this is not Facebook predicting what you will vote for. This is really a physical system where the equations are there, so there must be an underlying physics. It's not machine learning or something very high dimensional. And so we decided to do what is generally a modeling of the scientist. So we model the scientists, how they think, and how they copy each other in the development of their work. So we assume that there is an underlying potential energy describing where are the best material as a function of parameter that nobody knows. We assume that scientists will do experiments, and then if someone finds something good, they will probe something slightly different around what they found. So we have simulated what we call the research landscape to make sure that we don't have a limited number of data. So we assume that any research field will evolve in this way. The potential energy surface roughness is varied, the number of dimensions is varied, but the way people copy each other and follow the same path of others, swarm intelligence as some people call it, is common. So we have generated thousands of different research landscapes, like simulating data, simulating how people do research, and ask the following question: is machine learning useful in this case? Last slide. The answer was that depending on how adventurous the research is, so if people copy each other entirely or they randomly select molecule, we have the following situation. If people copy each other, machine learning is totally useless because people are looking in a restricted area, outside is not done, and therefore you will not know information about the outside world, and machine learning is not useful. It would be useful if people were exploring the material landscape randomly, but since they normally are in an intermediate situation where someone is creating, someone is copying each other, there is a window of opportunity where machine learning is useful. There is a moment where it is too soon, and there is not enough data to do your simulation, and there is a moment where it is too late. There is already enough exploration, and the machine learning is not helping you. So we have defined a machine learning game as what would you gain by adopting machine learning in your exploration after a number of data points are available, and comparing what you would achieve using machine learning and what you would achieve by following the business as usual approach. So in conclusion, machine learning using experimental data set for organic electronics, lesson learned, the data are repetitive, are redundant, without being exact copies, so we've challenged in training, defining training and testing set. There is an issue of overestimating the predictive ability of the model, given the data set that we have. Unless we do robotics and we do our own data, then we can address this. And it's also very difficult to improve the model using the Troisi descriptor, because the repetitiveness also goes probably into expanding the data set. So my conclusion is that we need to introduce machine learning, reflecting on what it means, keep the other option open, and whenever we realize something is not predictive, let's go back to physics. Let's never abandon physics.
Thank you, Alessandro, for a very enlightening speech and some, I think, reflection about or thinking about ethics here in the end, which is, I believe, interesting for all of us. Do you have questions? Yes, of course, please.
Thank you very much. I have two questions. One, have you considered sending a comment on your own paper? That might get you in the same journal.
No, but it's not wrong. And there's also in the issue. What do you do with the postdoc who actually did the work? It's really, I'm simply going to you specifically now, Johannes and this community. Let's be careful about it. So I'm very open, as you see. And actually, we send it to the journal. They don't like it, so it's not that I really try advertising that we didn't put under the carpet the problem and then putting on it good journal.
Of course, no, it was just energy. And so my question is about the last bit where you were modeling these potential energy surfaces of essentially experimental processes. So how do you know that the potential energy surfaces you postulate have anything to do with how real research works? I mean, because I think it is a very important approach, but it's also very challenging to model, like the sociology of how science works.
Yeah, so we did dimensionality. So the assumption that dimensionality is low is based on the fact that physics exists, so the dimensionality, so two dimension for the cartoon, but we went on 5 dimension in the thing. And we went roughness, which is how rough is the potential energy, so we have result depending on the roughness. And we also in the paper say if it's possible from the data set to estimate the roughness of the potential energy surface. So if you have 1,000 points, the idea is can you say something about the roughness of the potential energy surface, looking at what has been seen, and then predicting the roughness, deciding if it's a good idea to invest in machine learning. The goal was, suppose the technical question is for the director, shall we hire a computer scientist or a chemist for a particular problem? And the idea is a beginning, because it's not the final. How do we analyze the data to decide if it's now is a time for computer science or time for I don't pretend this to be the final, but I think it's the right question to ask, so I was hoping more people will come up with the right background to address this question.
Any more questions before coffee break? Nobody wants? I would just a philosophical question to some extent. I've been working not in organic electronics, but in solid-state ionics, and for quite some time now. And in all these applications, fuel cells, batteries, materials discovery or modern materials discovery has been to some extent a failure. So we are still using materials that were discovered decades ago by just using maths and material principles. Could you comment that? Do you think it will really help and could really make an active contribution to discover useful materials, these particular areas, for example? Because to some extent it has been a failure, I would say. Not very successful.
I like your question to be in everybody's head, and so we use this as a metric to define the success as we go. Of course, some colleagues can argue otherwise, like my colleagues in organic chemistry that use it regularly and publish on Nature, this is true, is it the case, or my colleague in molecular crystal discovery or like crystal structure prediction, they are successful. However, I always give the example of what is the main achievement of this laptop, which is the silicon device entirely come from pencil and paper. The liquid crystal of the display, again, thermodynamics, pencil and paper, and plastic, again, we have 2 Nobel Prize of plastic are all very good people rather than chemists, only one. So we have a history of success in science without machine learning, so we need to recognize that. And let's not forget about the periodic table, which is the best achievement of rationalizing the chemistry into a table. I would use that as a challenge for a computer to look at the chemistry known in 1840 and come up with a periodic table. But we have a metric now, and we can tell if it's useful or not. And so, for example, for inorganic, the usual metric is compounds containing 5 elements will escape any possible rationalization, so maybe that would be one way to go. And in this case, I propose a metric, which is can we discover a new receptor? I failed on my first attempt, but now, since I have a metric, I will be able to answer your question. So if we can, then the answer is yes, and so on. So if we ask the last question, let's not be happy about this correlation as we assume that. Then we have a question. So it's our duty to answer this question, and we'll do it.
Yeah, of course. I mean, that's the reason why you work on this fantastic work, but just thought. Okay, let's go for coffee break. We are with a little bit of a delay, but not that much. I think it's acceptable for an informal meeting. Okay, see you at half 11. Thank you.